Hello everyone, my name is Petra Tang. The title of my talk today is Predicting Gravitational Wave Signals from Compact Binary Population of a Milky Way-like galaxy for LISA. The outline of this talk is as follows, and I will elaborate individual parts. So what really motivates me is the fact that gravitational waves astronomy opens up new ways of studying the universe, and particularly in the millihertz band where LISA is guaranteed to detect signal sources. And before the launch of LISA, it is important for us to understand the physics behind it. Therefore, modeling of the sources of those signals can help us to predict potential signal form. What I'm using in my study includes the FIRE simulation, also called the feedback in realistic environment, which is a cosmological simulation of galaxy formation. And you can use this link to access that. It's a very useful and very comprehensive. As well as FIRE simulation, I'm using BPASS, or binary population and spectral synthesis code, as well as result to predict what signals LISA may see. This is a cutting-edge binary population synthesis code that is similar to Starbus 99. You can read more on the website. To begin with, we'll look at the theory. So we're probably familiar with the signal, which is the sum of the strain, H here, as well as the response function and the detector tensor here, D here, as well as a polarization tensor. So this formalization really tells you how to code. So if you put everything in, for each particle within the Milky Way-like galaxy, you can produce some modulated signal. So here, for the strain to work, we need the frequency, the mass of the primary and secondary star in the binary, as well as the location. And this comes from the binary population synthesis code, as well as the FIRE simulation. And the response function has the sky location, which you can pick at random, as well as the detector tensor, theta and phi, you can pick at random as well. So here is a result from the two binary synthesis code. I'm comparing studies from Lamberts, Astrid Lamberts 2018, black hole population, as well as 2019 white dwarf binary with the BPASS population. So here are the two several different combinations, but we are in this study, in this talk, we'll be specifically looking at the black hole binaries as well as white hole binaries. If you look at the number of predicted sources in the Milky Way-like galaxy, the number of black hole binaries are similar in both binary population synthesis models. However, the white dwarf ones, BPASS predicts a lot more, and we'll explain the potential reasons why this may be. So if you look at the mass distributions within the galaxy, with the distance here, x-axis is kiloparsec, and within about 10 kiloparsec, that's where you get most, if not all, of your sources. And you can see that from the two models, one from Lamberts, one from BPASS, the white dwarfs are consistent with each other, as well as the black holes. So, sorry about the color scheme, may be quite hard to see, but you can pause here to look at it. So let's look at individual compact remnants here. The first one we'll be looking at is the black hole binary population. On the left-hand side, you have the BPASS, right-hand side, you have the Lamberts, coming from the same or similar fire simulation, but the distribution, the mass is different, coming from different binary population syntheses. The x-axis represent the scale. You're looking at a kiloparsec, which means that this is actually quite small, it's right in the middle. And where you looking at the majority of the graph, it's actually just the halo. And you can see the individual satellite galaxies or maybe global clusters, wherein, if you recall the table, that they both share similar number of sources or number of particles in the galaxy. However, in this case, the right-hand side model spreads out the mass distribution, spreads out a bit more into the halo. What does it mean to us? If we look at, so this one we're looking at are the signals purely within, they're the signals for all spectrums of the gravitational wave signal. And here, that's the chirp mass. So what you're looking at, there's a frequency versus chirp mass on the left-hand side, the y-axis of these two models. And the reason why you see a huge difference between Lamberts model as well as BPASS is because BPASS here includes all metallicities. So Lamberts here only included the solar metallicity, where Z is 0.2. But if you look at where within the laser band on the right-hand side corner, they are pretty consistent. They means that we are potentially having those sources within this within laser band of the black hole binaries. However, BPASS also provides chirp mass at higher chirp mass within the laser band as well. It'd be quite interesting to see what Lamberts binary population synthesis model for other metallicities. So here I've cut the signals within just for the LISA frequency band of the 2-year mission for LISA, a time series. Vertically, you have your string signal, and you can see it's modulated where when the instrument is facing the galactic center. So in this plot, you can see that BPASS predicts a slightly less strength for the amplitude for the black hole modulated signals, and that can be the result as how the mass is distributed, and in turn is a result of what the physics tells us. As BPASS has considered more details of how binary forms, including the star formation history as well as metallicity evolution in its making. Now, if we move on to white dwarf binary population in the Milky Way-like galaxy, you can see they're slightly rotated, but nevertheless, we can see that the BPASS indicates there are more sources towards the halo compared with the Lamberts 2019. As well as this, we're looking at only the LISA band. We're not looking at anything that's lower than 10 to the negative 5 hertz. Similarly, if we look at the frequency to chirp mass plots and compare these two models, where Lamberts ones has a cutoff. They excluded anything that's lower than the lower band of LISA frequency. But here I'm just putting in the BPASS prediction just for comparison. So here that, keep in mind that Lamberts ones only includes the solar metallicity, but BPASS has everything in it, pretty much the whole shebang, the whole population. So it's very interesting to see within the LISA band, you get a lot actually of signals here, which is to be expected. And here's, again, I'm cutting just to look at, cutting the signals just to look at the frequencies within the laser band. And on the contrary to the black hole binaries, the in here BPASS is produce slightly stronger signals than Lambert's predictions. So here is it's very brave. Go through a very brave talk, only 10 minutes, unfortunately too short, talk about the details of how this come about and what I'm going to do with it. So what I'm currently doing is to extract the signals coming from other compact remnants, such as black hole, neutron star, neutron star, neutron star, neutron star, white dwarf, as well as I didn't write it in here, black hole neutron star, which is a very interesting source, and it'll be discussed in my future work, as well as the living binary populations. So this is the extent of this study, as well as I will be including noise in all the signals, because at the moment, what I've been showing you are only the pure signals. And to move on from that, another goal of this work is to be able to estimate spectral densities of those signals, because there are just so many of them, they are quite random. So the stochastic gravitational wave background are important to study as part of my research. And I'm hoping to develop a semi or non-parametric methods to estimate those signals. All right, so here's some of the references, if not all. Hopefully I didn't miss any. And thank you very much for listening.